Well, hello 535 people, this is Dr. Keith Schubert, and we're going to be talking tonight on complexity. This came out from because in class a bunch of people were saying that they would like to know more about how I was getting the complexity of matrix multiplies and things of that sort. So whenever we start off and want to think about complexity, there's a couple ways you can do it. And the way I suggest, particularly with matrices, is just think of how you're actually doing it. And in my classic style, I suggest that you do it by drawing a picture first. So imagine I am multiplying two vectors. And these vectors have 1 down to n elements and 1 to n elements. So if I'm doing two vectors multiplying each other, remember, the first element multiplies the first, second multiplies the second, all the way down, and then you add them up to get a single number at the end. And that single number is the result of n multiplies and n minus 1 adds, which means to get that number, you need to do n multiplies plus n minus 1 adds, which is 2n minus 1 floating point operations, which therefore means this is big O of n. So vector multiply, you have big O of n. Now if you keep this in mind, however many elements you're going across multiplying, that gives me a big O of n for one of those operations. Alright, that's one thing. Let's consider another situation with a vector multiplying another vector, except this time we'll have it be a column vector times a row vector. So again, we've got the same size. 1, 2, all the way down to n. 1, 2, all the way down to n. Now, in this situation, to get a single element, it's the first element times the first element here goes into this spot. So only one multiply is needed for that single spot. As a matter of fact, for everything that you go through here, this second one is second element times that one's first element, so on and so forth. When you go through and look at each one, you'll find out every single time I do one multiply. And how many elements are there? Well, I've got n elements this way, I've got n elements this way, so there's n squared elements inside this whole thing. So that means there's n squared multiplies that have to take place. So this is big O of n squared. So notice, it's kind of interesting, when I do it this outer way, it's quite a bit more expensive. And the big thing is also actually in spatial complexity of what ends up. This takes n squared elements to store, whereas the other one just took 1 to store. So spatial complexity is also important. And all we're doing at that point is looking at how many elements are there that we are storing. First one we ended up with a single answer, obviously big O of 1. This one we end up with n by n, obviously big O of n squared. Now, that's how we go. Now notice the difference between them might look, wow, they're two vectors. Well, in the first case, all we did was we multiplied each element by the respective ones. And that's essentially what the diagonal is. So if you took this matrix that we end up making, you know, you got the 1 times 1 here, you got the 2 times 2, all the way down to the n by n. If you summed up the diagonal elements of multiplying this way, you would have the inner product. But then we have to calculate all the cross terms here, where we didn't have to calculate any cross terms in the other one. So that's why this one is quite a bit more expensive in both cases. Just as a side note to you, summing up the diagonal elements is actually a very common thing to do. It does have a lot of cases it comes up important in matrices, and it's called the trace of a matrix. That's usually abbreviated TR, and it's a trace of a matrix. Okay, so this is vector times vector things, the two ways you can do it. So notice we got one that was big O of n, and the other one big O n squared. Let's go on to vector times a matrix. So imagine I have a single vector, and now I'm going to multiply it by a whole matrix. And let's say this is 1 to n And we'll just make this one square at the moment. It doesn't actually have to be. So I'll just continue my 1 to n. Okay. When I multiply them, the answer is going to then have n, because I made n columns this way as it goes. Now, what does this end up being? Well, to get this one, that's what we did before. That took 2n minus 1 operations. This one right here is an identical operation, this times this. It will also take 2n minus 1. Realize I'm not saying those are necessarily the numbers, otherwise I would just take it and copy the answer and be done. But, these are some numbers in those spots. So obviously I'm doing the same number of operations to get every element in here. Each one of these takes big O of n to calculate, and there are n of them. So that means it's going to take me big O of n squared to calculate a vector times a matrix in this way. So again, we see kind of neat operations as we're going on. Now what would happen if I extended this? What if I did a matrix times a matrix? So now imagine two n by n matrices. So again, every time to get this element, it's this vector times that one. This one is this vector times that one. This one is this vector times that one. Every single one of these occurrences is an inner product, and it takes big O of n. Right? But now, instead of there just being n of them, right, to get a single row, it was big O of n squared. So an individual element was big O of n, the entire row was big O of n squared. To get n rows, I have to do that n times, which gives me, for the entire resulting matrix, it's big O of n cubed. So matrix multiplication is big O of n cubed. So that gives you basically the way you can do it. It's just adding up. Spatially, this takes big O of n squared elements, right? Because there's n by n, so to store this, big O of n squared. So anyway, that gives you some ideas of how to do these ballparking things. Basically, what I'm doing is figure out the work that it takes for one element, and then I extend that by figuring out how many elements there are that I have to calculate. So hopefully that helps you a little bit on how to ballpark and calculate. Well, actually, this isn't even ballpark. It's how to easily be able to calculate your complexity of your multiplications. So I will see you all in class next time. Have a good day.